Okay, welcome to the first one of the parallel sessions. It was a great morning keynote. And so I'm very fortunate in terms of this session to be able to introduce my friend and my colleague, Dan Garcia. Dan's very, very high energy, warning you in the front rows, keep your toes tight. If you've got any seeing eye dogs, keep the dogs underneath the chairs, sort of stuff like that, because Dan has a lot of energy and you will absolutely feel his excitement talking about using the magic to teach introductory computing. Dan was an undergraduate at MIT 100 years ago. I'm his age, so I can say 100 years, 98 years ago.
I have more gray than you do. So
but I'm 2 years older. Then did his PhD at Berkeley, liked it so much he decided to stay around. He is a tenured teaching faculty member at Berkeley. I think there's a term SOE or something like that. I forget what that stands for. But that means he's a tenured professor who's hired primarily because he's a wonderful teacher. You guys are about to find out why he's a wonderful teacher. And I'm supposed to read all these accolades for Dan. He's just an awesome guy, does some really cool work, was involved with CS Principles, is involved in CS Principles, and only a gazillion other sorts of projects. I think I'm looking forward to his talk. I'm going to be sitting in the back enjoying because I know he has enough energy. I'll hear him in the back, and I don't want to get my toes jumped on. Dan, turn it over to you.
Thank you, Steve. That's wonderful. All right. I always feel introductions like that. It's like going to see Pacific Rim, this new movie, and if your friends say, it's the greatest movie ever, and then you go and it's not the greatest movie ever, and you say, it's terrible, even though if you hadn't heard that, you would have thought it was a good thing, right? So don't do that so much next time. So this is a session, if you attended my SIGC 2013 session, it's the same essential thing. I'm kind of shifting some things around, but mostly if you've heard it before, feel free to go to another session if you've heard me do this before. But this is mostly, we presented in SIGC 2013. My co-presenter at the time was David Gannat from Tel Aviv University, and I'm going to have my student, who's coming from a late meeting, join me for some of the double-teamed magic sessions we're doing. So this overview is I have 7 amazing magic tricks. These tricks are useful in outreach. These tricks are useful as unplugged activities. These tricks are useful when you want to decide to teach the concepts you normally teach with programming or with something on the board with a really fun thing that engages your class. And one of the reasons it engages your class is you do a magic trick and the kids look at you and if it's a good magic trick, they're wowed by it. And then they want to try to learn how to do it. So it really pulls them in. This magic really pulls them in because they want to solve that nut. They want to crack that nut. And once they do it, then they can perform it to their friends. And it's often great to see students performing the same trick to their friends, which is really awesome. So the key thing here, we're starting motivation here. And this is being filmed, so you'll have this on the CSTA page years from now. Magic is fun. Magic can be much more than fun. And I'm not doing any sleight of hand magic. This is all magic with CS principles underlying it. So it's not the CS principles, the movement and the CS10K movement, but CS ideas underlying it, all of these things. So here are some computing notions. There's often discrete math that comes in here with permutations. You often are thinking about the problem representation. Once you kind of reveal usually the model, by the way, usually is I do the trick, and then we play with it some more, and it's questions, and we have a nice little discussion-y thing where we might want to try it. Maybe have some volunteers try it, blah, 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 blah. If some smart person thinks they got it, I don't just let them say the answer, because that kind of spoils it for everybody. I let them whisper, and they say, yeah, now you try it. And then they'll try to create the magician's version of it. So then they try to do it for the class. And then one by one, they all decide to become the magician, which is really fun. So you don't let them kind of just out, oh, I got it. It's under the sleeve. No, it's not. Don't just give it away like that. You got to keep it. Algorithmic patterns, certainly everything I'm doing is an algorithm. I'm going to do a magic trick, and there's an algorithm behind doing the magic trick successfully. So there's certainly pieces of how that works. And there's some general notions of maybe symmetry and some other pieces of the discrete math that comes in there. In terms of problem solving, folks know the Exploring Computer Science movement. There's a wonderful curriculum. It has 6 units, and one of the units is problem solving. And some of I'm the champion for our local CSTA chapter, and I made that title up. It just means I'm the guy who reserves the room. That's all it means. But I love our CSTA group, and Eugene Lemon, who's around this week, he's our CSTA president. And one of the things that he says when he was teaching ECS, the best chapter of all, there's a programming chapter in Scratch. That's wonderful. There's robotics. He loves that one. There's HCI. There's web design. He says the best chapter, the best module is the problem-solving one. Years later, that's what they'll take out of that class, he believes, is the problem-solving. We heard that in the keynote, right? CS is for problem-solving. So here's what you use for problem-solving. Decomposition of a problem, thinking of it in smaller pieces, simplifying it, generalizing it. There's abstraction coming in, obviously. Backward reasoning, analogy, and representation, again, coming back in here. So enough with the setup. Show me a trick. All right, here we go. So the first one is I'm going to do a real-time magic square. Have you heard the magic square before? The magic square is one in which I can add up all of the rows and columns and have them come to n. That crazy thing? How's that possible? You're going to give me a number, and I'm going to have the magic square eventually have all the rows and columns and diagonals add to that number. Is that possible? It seems too hard. It seems impossible. So you're going to give me a number. Let me see if I can get my thing. Let me unplug for a second, and let me get this here and make sure that I have got the right slide here on this one. Let me get to this. Sorry, I'm going to get to this one here. Okay, so think about a number you're going to give me. You're going to give me a number from 25 to 100, okay? 25 to 100, and I'm going to do this. And I'm going to do, is there a little sheet of paper? Can I borrow a small sheet of paper? There's a small little, I'm going to borrow that for a second. There's a small little trick. I want to make sure that I get this right as I get the trick right. I've got a small little trick here as I do this. So think about your number and how is it possible? Most of you have seen the 3x3 magic square. You know, you do the thing and it's and it's analogous to tic-tac-toe and all that. How is it possible that I'm going to do this for 4x4 for any number you say? That somehow doesn't seem possible. So how is that possible that I'm going to do this for any number you say? I'm just going to make sure my slides are good for there. Okay, I'm hitting this there, just making sure my slides are good. There, okay, so we're back. And we're back, as we say. Okay, so, and who has a number for me that I can... Put this like this, okay. Okay, yep, there's that. And I'll go to here, boop, okay. So I'm going to try to do this and see if you can see this from the back. And I put this right here, okay. So give me a number some in the back. Yeah, go ahead, give me a number. So 42. So here's our number 42. 42. Now I'm thinking about how to do this. Thinking about it. All right, so 42. Well, 22 is a good starting point. And then a 1. Okay, so see, 22, I have to make this work now. 12, I'm just doing this from here. 7, okay, so does that work? Let's see, 22, 1, 12, 7. Are we doing here, okay? Yep, 20, 42, got that one, okay, good. Now, if I do an 11 here, then 11, and if I do a 20 here, I'll get my 42, right? So how about a 5 and a 4? 5 and a 4, does that work? There's my 20. Okay, got that one good. Maybe I'll try green if green's a little bit brighter here. This pen's a little bit bad, okay. And now I gotta do this row. So 11, see 42, well, 21 looks good here. So is this a little bit easier to see? 22, okay, 22, 1. So far I'm good, right? So far I've got a row and a column. Okay, 5, here's my 4. Okay, 21, this is now 32, so this has to be 10. So how about an 8 and a 2? So I just hope it all works by the end. That's the one that always is the key. If this just works, how am I going to do this now? So now let's put a 10 here, and let's put a 3, and what do I need to get? It's 18, 42, what does that have to be now? 24, right? Is that right? 24, does that work there? So 18 and 24, that looks like 42, okay. And then, what do I have? A 6 and a 9. That's 19. This looks like it has to be a 23. Now, let's check it out. Okay, let's check it. See if I got it now. Okay, here we go. So, 22, 20, 42. Who did do fast? I assign each of you a different row. Top row, second row, third row, fourth row. Here we go. Left column, next column, this column, this column. How about putting it back? Diagonal here, ooh. How about this diagonal there? Do they all work out for 42? Let's see if we got this. Thumbs, 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 thumbs. 42 magic square, ladies and gentlemen. Okay. Now, let's do some fun things. Let's look at this top square. What does that do? 22, 30, 42. Ooh, a little gift on the side. I didn't expect that one. How about this corner? Let's look at this one. Let's see. 20, how 42. How about this guy? That can't be right for all of them. That's impossible. How about these guys? 24? 40. Wait, and how about this one here? Hello. Are there more? Are there any more? We can't. I can't. That certainly can't be them. I mean, this also can't work. Also, there's no way this one works. And then, come on. How about the corners? I mean, there's no way the corners work. Let's see, 22, 26, and 16. Now, is that right? 42. What's the thing? The top four in the middle work. The top four right here. Look, this works also. Come on. That can't be possible. And the bottom four of the thing. And the thing. It's gorgeous. The side ones don't work. Well, we did pretty well. We did pretty well. Now, you gave me the number. Were you a plant? Let's have a conversation. Was that a plant? That was a number that could, I mean, honestly, it can work. Any number, 25 to 100, it can work. And there's some math things. It actually works with any number you give me. You gave me pi, it would work. It revealed what I'm doing a little bit with pi, but it actually would work with pi, too. All rows, columns work with add to pi. Crazy. So, does anybody think they know how to do it? Anybody have any? This is now where you open up and you say, any student want to come try it? And I give you a number and you can make it happen? Anybody have any idea at all? Let's talk theory. Let's talk theories now. Now that there's none of that, let's kind of talk about how is that possible? Yeah, go ahead.
You have numbers 1 through 12 at standard locations, and then you add up the last number in each row.
Oh, so I like that idea. So I have 16 spots. 1 through 12 are kind of, you see the numbers 1 through 12 in here. And then it kind of jumps to 4 special numbers in the 20s.
Whatever makes it work.
And whatever makes it work. And I really like that. And let's even look where those numbers are. Anybody heard of the 4 queens problem? 8 queens problem on the chessboard? Does this look kind of 4 queensy, where none of these queens, except for here, I guess, maybe, but none of the queens shares any row or column with each other. So I like that. That's excellent. One of the students, I mean, what else would work? If I said 25 to 100, it also would work that I've literally memorized a 16 by 16 grid of numbers times 75 of those different possible grids. That's possible too, and that would work, right? That would be the fastest one, and that was the lookup table, and I'd have that. That's totally reasonable, but not something my brain can hold, certainly. So it has to be some kind of a pattern, some kind of equation. I like it. Well done. So I don't want to dwell because I've got 7 of these, and I've got to somehow squeeze these all into an hour, and we may end up throwing away some of the easy ones. So all of these add to n somehow, some magical way, and you saw there's a lot more n's. This is a nice little animation I created. So a lot more n's that are created from this. And by the way, this comes, I always want to give credit to the source, this delightful book called Math Magic. It's really computer science magic, but it's math magic too, and I grabbed some of these problems from there, so I want to make sure to share the love of that. So here, my friends, is the revealed magician's trick, which we only do within fellow magicians, and you're now all blessed as fellow magicians, so I can reveal the trick to you. If you were, Vegas folks, I wouldn't necessarily do that. So watch this. This is a wonderful pattern, and this pattern guarantees for any n that this works. Let's try it. N minus 20, the remaining numbers add to 20. So whatever n is, that adds to n. Isn't it a beautiful kind of way to think about this? And similar here, every row adds to n. So if you do this, every single row still adds to n in the original way, and I'll skip you the animation of that, but it just works. And what you can also do is you say, look, n minus 19, all I need to find is 3 numbers that add to 19, and that now adds to n. So 6, 10, and 3, there's my 19. It also turns out that any other 3 numbers I can get to 19, like look, 4, 5, 4, and 10 add to 19. Or I could say n minus 19, here's an 8, and now I have to have 2 numbers add to 11. So I can say these 3 work, but that's a weird shape. That doesn't work. And so you try to find things that are there. So the point is, there are many more patterns that add to the thing that aren't just boxes and squares and lines. If you can find anything that adds to 19. Here's a 19, here's a 9. Well, then a 6 and a 4, we got that one. Also a 7 and a 3, and so any two things add. So the point is, you can make out of these patterns that all do the same thing, all hold in a certain pattern if you wanted to kind of make the argument that way. So you're actually, this is a really wonderful thing. You can ask your students to program this. Intro, make a block, make a early hello worldy thing, but it takes in the value of n, and it spits out, just printf, ASCII table, of your magic square. Very easy. Very, very easy program. I think Stuart does his fun thing of making them do a rocket ship where of different sizes. And the bigger the number, the taller the rocket ship and the wider the rocket ship in some kind of triangle thing and have to figure some equation thing. Same thing, right? You're just printing numbers and you just replace the n minus 20. You just say printf n minus 20. Whatever n is comes in, you print that in that field. And oh, wow, this magical thing will give you a thing. And how does it do it? How does it do it? That's the simple pattern, okay? So the mechanics of doing this, the secret, by the way, the magician's secret is if you're doing this on stage, in pencil before class, you write this answer in all of the slots in pencil, really, really fine pencil. No one can see it again except you. And as you're writing the pen, you make sure that every one pen mark hits just the center so that you end up covering the pencil that had the answer. So the student goes up like, how did you do it? And then they can't see the fact that you wrote over your pencil mark. So that's the key thing of that. So just some, from magician to magician, here's some good tricks that you can use for that. Here's the beautiful thing. You've got a correctness proof here, right? I've kind of proved that this works for any n, including pi, including a complex number. It just works. It adds to, all those rows and columns and diagonals add to n for any n. So there's a correctness proof as well. And the value of randomness. Here's the value of randomness. I'm going to do this trick 3 or 4 times. I don't always put it in this pattern. There are 8 different rotations and flips, just like the 8 different rotations of a tic-tac-toe board. This tic-tac-toe board is the same as that one, is the same as that one, is the same as that one, is the same as this one, and that one, and this one, and that one. So if you're very clever, you say you want another, let's do it again. And you flip the paper over, and it has it written with this flipped and rotated. So it's not the same. They're like, wait, there's a 7 and a 12 here, but that's now down here and flipped, and they don't see the pattern. So the value of rotation in terms of the showmanship of this is you flip it a couple times, so they don't really necessarily always get that it's, The problem is, if n gets really big, as you kind of was here, if n deviates from, about 40s and up, if it stays in the teens, then you've got some duplicate numbers and it gets interesting and it's hard for them to deduce it. If they say 100, I said 25 to 100, remember? If they say 100, then these become, 80s and they stick out like sore thumbs. So you can change this by kind of limiting it to pick a number from 10 to 30, and it's still impressive enough, and then it's harder to find out. So just if you really want to make this harder to conclude, keep n between 10 and 30, and you still get it good. Other questions about this before we go on to the first one? That's the first one. This is called the magic square. It always works. It's great. A nice fail-proof magic trick. All right. So there's my ends, and I love it. All right. Let's go to the next one. Bink, 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 bink. And boom. This is awesome. This, if you haven't seen this before, you are going to love it. Here's how it works. You get 2 to the n integer cards, and it also could be random numbers. So in fact, I'm going to ask you for small random numbers from 1 to 10, okay? 2 players are alternating turns. Each player on her turn takes a card from one of the left ends. They take the card, and it's their card. We're going to do it in the front, just so you can all see it, with numbers on the side, and you'll just claim it for yours or for me. Okay, so it's like, as you take the card, it's yours, or I'll take the card for me, okay? And my assistant, I wish he were here, but he got stuck in traffic, but he'll be here for the last one. The winner is the player whose sum of the end cards is the largest. I'm sorry, the purple and blue doesn't work so well, but the winner is the person whose cards is the largest. Okay? So I'll do just to give you an example, just to give you a very, 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 very easy example. Let's just borrow this one. And if I were to write, let's say these are my 4 numbers. Let's say this is my card limit. Okay? So you and I are going to play a game, and I'll take the left card. By the way, here's how it's going to work from the magician point of view. I'm going to look at it briefly, and then I'm going to stand behind here, and I won't have any idea what's happening. I'm somehow going to memorize the whole thing, and I'll tell you which side to take it from, and then someone in front will volunteer to come up and grab each side of that, and I will just memorize the perfect pattern to do, and I will always I will never lose. I'll either win or tie. So look at this one. So if here, I would go over here, and I would look at this, memorize it, I would say left, which means this would go to Dan. I'll say up is me because it's over the top, okay? Then now, I took this card. Now you have a choice of this card or this card. You can only take from the ends, okay? So now these two cards are revealed. And you'd probably say, I'll take a 7. So this is you get a 7. I had a 22, you get a 7. And I would look over here and say, I might say right. And that will give me the 12, and so I'll get this sum, and you'll take the 1. And so you'll have 8, and I'll have this, and I'll have 1. Does that make sense? But this might be set up because I get to go first. So that means I get the big one. That's too easy. So as we're playing this game, I want you to be thinking about giving me, you want to pick 10? We can pick 12. It can be any number. I can do 100. That's what's cool about this game. I can do 100. I can do 1,000. You write 1,000 numbers here. I'll look at it, do a little calculation, and I'll sit back here, and I will tell you left or right for 500 moves. Not seeing the board. 500 moves, and I will guarantee not to lose. I'll either tie or win, and most of the time win. And in fact, I'll even go you one further. I'll tell you how much I'll win by. I won't tell you the final sum, but I'll tell you I will win by 3. And you're like, you did not just predict out of 1,000 moves to win by 3. I said, yes, I did. You want to try it? Let's keep it. How about let's do more than 10? Let's just be interesting. Let's do like 20. You want to, really, 20 numbers. Let's do 30. 30 what? I mean, really, anything. I can do anything. All right. So I need small numbers, because if you do like 50, it's kind of hard to do the math. So give me small numbers from kind of 0 to 9, and just random numbers. Give me a random number 0 to 9. 8. Remember, is anybody plants? I mean, let's be honest. Are we plants here? Are we friends or are we plants? You're friends. Okay. 8. So this would be my sum up here, and this would be your sum down here. Just do this. And I'm going to do this left to right. So this is kind of wrap like this, as if connected. If this makes sense, it's like this, and it'll go like this, and then this is really over here, and this is really over here. So it's really a one long line, but in a boxy thing. Okay, 8. Just play that. Okay, 8. Go. Random number 0 to 10. 0 to 9. 3. Okay. 0 to 9. Troublemaker in every audience. I'm telling you about it. 9. Okay. 9. Fine. Go ahead. Keep going. 5. 7. Which one? 5? Okay, 5. Have to be an even number because we each have the same number, so I need one. Okay, keep going. So this, remember, this really wraps to here, so it's really one long line. Okay, keep going. Yeah, go next. 2. 1. 0, that's fine. Let's keep going. 1. 7. 6. How are we doing? 1 to 2, 2, 2, pairing, but one more. Last one. 4. Okay. Piece of cake. These are really connected, okay? These are all connected as one long line, so make sure. So when I say left, this is the left side, this is the right side of that thing. So if I take the 4 away, then 6 is revealed, right? Yeah, make sense? You get that? Okay. So let me see here. I'm looking at this randomly. Feel free to stare and see what you can calculate. I'm going to just stare at this for a second and look and see what I can do here. So, and he, and then, ooh, this is really interesting. I think, wow, it's really, really close. Oh, I like this. I'm going to do it again. Ready? Hi, and then he, and hi, he. Wow. That's just great. I'm going to win by 2. 2. That's how much I'm going to win by. Okay? That's it. Okay? Here we go. So I need a volunteer. You be my colleague is not here. I'm just going to say left or right. I'm not going to look anymore. This is your game, my friend. I'm standing back here. Okay? Ready? And I'll take from this side, which means you take this top left number. You kind of write it up there in my upper area. So cross the 8 off. Yep, cross him off. And then show the group. And you guys can pick. You just say left or right. This is. Right. You choose. You talk about it. Talk about it. Right. You want this side? Okay. I'm going to go with the. wait, let me think. Okay, 5, 6, 7, 12, 3009. This side. Okay, I'll take this side. Yeah. So you go grab that number bottom there, cross it off, and add it to me, right? So far? Is he doing the right thing? Okay. Call it. Okay, right. Okay, I'm going to take the left. No, wait. No, this time. Okay, this time it's the right. Okay, just the right this time. Okay, go ahead. I almost did the calculation wrong. I can't see. I have no idea what's happening, by the way. Okay, that's easy this side. I want this one. I want that number right there. That's key to my whole thing. Oh, that was easy. I want the same. I want the next one. Keep on the same line. I like that same line. That's good. That's good to me. Go ahead. That was really easy. Okay. Yeah. So far, I'm going to take the right. Oh wait. No, wait. Yeah. No, the left. This one. Not this one. This side. This guy. I was going to take that. I almost messed up. It was this one for another thing. There's another game I play. It's this side. Yeah. This side. Yeah. Okay. That's easy, this side. That's really easy, this side. Are we done? How we do? 10, 20, 34, 35 for me. How much you get, folks? 10, 21. 21 and 11 is 30, wait, 32. I won by 2. Are you 33 or 32? I won by 2, right? Let's do it. 10, 32. Oh, I must have done something wrong. I must have added wrong. Okay, I won by 3. I added wrong. How about that?
You did win, but there was one turn where you took the smaller number.
I did. I wanted to keep. I wanted to. I was looking at the future. It looked locally a small number, but larger scale, it was the bigger number.
So would that get messed up if we didn't pick the higher number?
No, you can do anything you want.
What are you doing now?
Exactly. Oh. No, just kidding. Oh. Isn't this juicy? I mean, what makes a great magic trick to me is that everybody's engaged, which I thought that everybody was, right? I was looking at you from my position. And when it's all done, you have no idea. So now I've hooked you. I have totally, and you're in. You want to be part of this. You want to figure out what it is. You want to find out what CS principles behind this, because we're in a CS class. There's this awesome magic trick that I love. I can't figure out how it works, and I get befuddled by it over and over and over. So it's pretty cool. I can even set this up where what I'm doing, what completely looks like the wrong thing to do by missing this huge number, but I'll still win. Like I can set it up with like I'll skip this 20, and then like I'll just end up at the end still winning by skipping this really big number. It's really kind of fun. Well, I want to see if anybody has any ideas. Now we have a discussion. I'm not going to just give the answer. This is where we simulate a class. This is modeling, and so give me some ideas. What are some strategies? Go.
The difference between your number and our number.
Okay, go ahead. Tell me that.
Something like that, because you chose an 8, we had the 4, so there's a difference of 4.
Right. Okay, I like that one. Yep.
In your favor.
Yeah, that's true. Plus 4 to me. Plus 4. We can walk it through, right? Plus 4 to me. Plus 3 to me. Plus 1 to me. Even. I'm now losing by 1. Now I'm up by 2, and then I'm up by 3 at the end. Yeah, I ended up adding, I forgot the 1 at my sum. So I ended up winning just at the end to get the thing, right? I can do it fast. I can do it fast. If you get 1,000 numbers, I could basically walk across. This is my speed. I would go, Walking, as reading across, done, 1,000 numbers. I mean, I have to see every number. I have to do a little bit of calculation at every number. And then I sit back and I can do 1,000 numbers. I'm not joking. I can do 1,000 numbers and still predict the answer, win all the time, predict how much I win by. If I add right this time. Very good, very good. Is it similar to the game of NIM? If you haven't seen the game of NIM, it's a delightful game in which it appears you're doing magic, but you always win or you always lose. It is not in the Sprague Grundy family of NIM, but they're similar in that I can kind of always have a pattern to win. So that's the part that's similar, but it isn't similar in the NIM-y, like, binary equivalent kind of thing. Yeah?
Does it have anything to do with the fact that you always start and the two middle numbers, if I can see correctly, are 3 and 2? So did you figure out if you always start?
The two middle, you picked the numbers, 5 and 2.
Oh, is that a 5?
That's a 5 and 2. And you picked them.
I know, but I didn't know if maybe you just look at that middle number.
You want to do it again? I mean, does it help to do it again? We're a smaller set? Do you want to see the answer? There's no time? I mean, I don't know. No time. I mean, what do we? It's a lot, but this is one of the best ones. And the other ones are a little trivialer. You've probably seen them before. This is a really juicy one. Let's talk about it. The slides actually lead you through it doesn't give the answer. The next slide doesn't just give the answer away. So let's go through it to see if you want. So here's the magic. Oh, whoops here. Okay, the magic is the volunteer arranges the cards. This is if you do it with cards. Cards are also fun. You can take these cards. And they're not about, what I would do when I do this with cards is I buy 2 or 3 decks, and I only take the spades out. So it's only like the spades 1 through 9, just so that you have like the same. It's not like, oh, well, your suit is, there's some information with the suit and the this. You just put all the same, right? So it's all the beautiful cards together. And you scramble them, and you have some duplicates, and you have some fun. The kids can do anything. Scramble, and you go, okay, go. Left, right, left, right. I win by exactly this much. I mean, it works just like that. Okay, so one of the things, if you want to win, right, if you're just playing with a friend, one of the heuristics, the strategies you might take up was the greedy heuristic, okay, in which you take the larger end. And now I chomp off a big parse. So here's you're thinking of the 5 and 3, what do you grab? You grab the 5. But what do you reveal for me? Ooh, you give me the guy behind it, right? So there's a little question. So then maybe they say, well, what we usually have is students work through this heuristic. If you want to play this game, by the way, this is a magic trick. This also is a game. You can just present this as a game to your students and have them play together and see if they can come up with a heuristic on their own. So I'm just giving you a trick that way that I always win, but just have the kids play together and see who wins in a prearranged sequence of 20 numbers that the class agrees on. You go to the first 20 kids in class, they pick a set, that's the game for today, and you have them pair up and play, and you can then they go back and forth, and one person goes first the first time, one person goes first the second time, you figure out what you do. So you can have them play to engage them. And then you say, I'm going to play and never lose. They're like, no, come on, that's crazy. And then you go ahead and do it. It's really cool. So maybe look at the delta, right? They usually refine it, right? This heuristic, whatever, you just add this little feature to that heuristic, which is, here's a 5 and a 9, here's a 3 and a 3, that's a bigger delta, therefore you don't take the 5 because you'll be down 4 in the delta, but you take the 3 in this case, right? So you kind of give up the 2 versus the 3 versus 5, so you're kind of giving up 2 on that side, but this is going to reveal this big number that maybe is a problem. Maybe also you have some extreme value. Maybe there's like a 20 and the rest of them are small numbers, and you want to always get to that guy, so you never reveal the 20. So you keep burrowing away until somebody has to reveal the 20, and then the person gets the 20. Maybe it's about the extreme numbers, right? So where are they? Well, there's a 9 and a 9, so how do you guarantee that you get the 9 and the 9 in some kind of long-term strategy way? That's a little bit harder. You could also do this deterministically, where you say, well, let's solve the game for all pairs. If I just look at, okay, between 5 and 9, who wins? 9 wins. How between 9 and 8? 9 wins. 8 and 4, 8 wins. And now you try to solve for all triples. What if you had those 3 who would win? If we just the 3 of us play, boom, 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 what would you eventually get? I'd probably get a 9, you get a 4, I get the 8. So I get 17 to your 4 if I played locally, now we're going first. And you can figure that out. And then you go to all 4s and figure out how much would you get for the 4s. And you kind of build up this very interesting dynamic programming table of the 2s, then the 3s, and the 4s. And when you're done, at the top, that's how much you win by. And that's actually the clever way to do this, and that builds up a nice little tree. That's harder. Usually junior level students are working on that kind of thing. To program this is complicated. Dynamic programming is not easy to do when you have to build this table, and you got to work backwards, and it's complicated, so not as simple. So the game, let's think about, this is out-of-the-box thinking, divergent thinking is what we're kind of trying to encourage in problem solving. The game involves selection from alternate locations, so maybe look only at the locations, not the values. For a moment, let's think about the location, not the value. Ignore the values, blur your eyes. For me, which is easy, I'm blind whether I take my glasses off. I just see, cyan squares, rectangles, okay? So think about that. Now, the leftmost card is initially at an odd location. The rightmost card is at an even location. Okay? If I remove the leftmost card, I reveal 2 even locations. Right? And similarly, if I remove a rightmost card, I reveal 2 left locations. Okay? So, extend the pattern. If I remove the right card, if I remove my green, I reveal 2 what? 2 odds. Is there a guarantee based on that you can kind of see? Can you get to my next slide? Which is, I take the first card. Let's say I take green. Is it possible for me to eat blank the green? What's the blank word? I'm going to take the first green and then use some strategy where you now have 2 odds. You got to eat an odd. What if I like the taste of green? Is it possible to guarantee that I could eat all that was the word I was looking for, all the green? Is that possible? Yeah. Conversely, could I eat all the purple if I wanted to? I could. You've just told me that if I wanted to, I could eat all the green or all the purple. So what do? Add up all the greens and all the purples. And which is bigger? Oh, I don't know. The greens by 3. So I say, I'll win by 3 if I can add right. I'll win by 3. And guess what? I eat all the greens, and I win by 3. After I remove the card from the first location, the ends are green and green. I remove it. So here's a game scenario. I eat a 5. You got 2 greens. You eat a 6. I have to eat the purple. How do I know what to do? There's 1,000 squares. How do I memorize 1,000 squares? You got 2 purples. Or you got 2 greens. I want to eat all the purples, right? In this point, I want to eat purple. I grab purple. There's 2 greens here. Which one do you choose? The right. Which one do you reveal? The right. What's my strategy? Take the right. Or generally, just copy you. You didn't know that. Maybe you saw it. Maybe some of you may see it, by the way. I tried to move it around. I tried to give you enough of this one. No, wait, this one. I tried to give enough of I was thinking about it, so I didn't just go left, right. It wasn't so trivial. I tried to play a little bit of the actor on this side, but all I was doing is copying you, which I could do for 500 moves easily. And I would win by my 3 I predicted 1,000 moves later. Isn't that cool? Now, it doesn't guarantee me the biggest win. Dynamic programming would. If I did that and looked at the which left and which right, that would tell me the right way to do it. Okay? But this strategy is enough that I will never lose. If they're tied, then I'm going to say, we're going to tie. They're like, you can't tie. I said, yes, we're going to tie. So if they end up just so that they tie, you can say, let's add 2 more, and you add a 0 and a 1, right? So that you can be up by 1 and make a choice. But the point is, you can at least say, I'll never lose, given my strategy, even though if I played perfectly, I actually might be able to win this game. I'll say my strategy is I'll never lose, and I do it blindfolded, and it's great. Huh? What are they? Okay.
You always have to go first, though.
I always have to go first. That's the key thing. That was part of their whole rules. I'm going to go first. I'm on stage. I'm standing up. I'm going to go first, and also I'm never going to lose. That's part of that. Isn't that great? Do you think you can do this now? Is this enough of a takeaway that I've given you enough to be able to walk away and now do this to your friends? This is awesome. You'll never lose. I love games that you can't. NIM is like that. Like NIM is one of those games that literally I can play NIM all day and just never lose. And I can also, NIM is I can switch it. I can force you to win. I can actually force you to win, which I can do it here too. This is like NIM, I can say, you know what? I'm going to lose by 2 on purpose. Like, no way. And you try to lose, and I will force you to win by 2. Isn't that cool? Like, we can flip it, and I can actually guarantee that I'll lose by exactly that much. That's really neat. Yes?
So you have to be able to add very quickly.
Aha! You have to add very quickly. How do you add very quickly? Do you think I'm adding, let's do it together. Am I adding them all up and subtracting these two big numbers? No. Deltas. It's all about the deltas. Let's try it again. 5, 9, right by 4. 8, 4, tied. 7, 5, left by 2. 1, 2, left by 1, because 2 beats that. So I'm adding deltas. I'm adding every competition. 9, 6, that's 3 to the left. And that means I take my 1 and add 4 to 3 to 1. I get 4 now. Left by 4. 3, 6, that means right gets 3 more points. I subtract 3. I now have left by 1. Doesn't, well, I'm reading across. My point is, you don't ever play with 1,000. You pay 30 or something at most on that real thing. But I could do 1,000 by just doing these deltas and walk across and say left 2, right 1. I'm basically saying 9 to 8, left is winning by 1. And if the next quarter, or the next period of scoring a game, right scored 7, left scored 4. If left was winning by 1, this difference is 3. So this is up by 3, this is by 1. I then cancel this, become this by 2. Like I just basically am doing that. I'm just going to continue a rolling, continual who's up by how much if this is the scores over the, every time they shoot a basket or something. So it's pretty fast to do this, the deltas. When I first did this, I tried summing, okay, 9 and 4, 13, and 5 is 18. It doesn't work that way. You can't add that fast. But you can add much faster by doing the deltas. It's great. Love it. Love it. Yes?
Two things. Number one is your strategy for adding up is similar to card counting.
Oh, interesting. I didn't know that. Okay. So there's a card counting, the person on the recording, similar to card counting in my algorithm for adding things up.
Up until last year, the New Jersey Institute of Technology ran a high school program.
Go ahead. Just so you can hear.
The New Jersey Institute of Technology used to run a high school programming competition, and this was one of the problems several years ago.
Oh, nice.
So,
That's great.
and what we did is we tried to do a deterministic solution.
Sure. Yeah.
Yeah. And it was hard.
Well, it's hard because the default you're going to do is you're going to build a tree of all the possibles, your choices and my choices. You got 100 things there. That's 2 to the 100. You can't do that. You can't build a tree that big of, like, here's all the ways you could play, with all the possible sums you could have, and all the sums I could have. That ends up being a binary tree that forks at every possible extra new pair of numbers. It grows exponentially. That's why the dynamic programming table-based solution actually is really clean. Who wins for every pair? Who wins for every triplet? Who wins for every quadruple? You keep working up to who wins for every size 20, and it actually is not bad. It's no more than a squared solution. That's really quite nice and really fast. That's the fastest way to do it. Good. So that's the game. It's called the odd-even game, or the left-right game, and it's just really wonderful. So it's good to, in general, as a summary, it's good to play as for kids. It makes random numbers, and then have people pair up and play, and who wins, and talk about that, and that can lead to a programming challenge and some other fun. Or you could play this as you come in at the end, and you come in and you say, there's a magic trick here too, and you play the magic trick and you do the magic trick. So you can either use this. This is very meaty. It's a wonderful puzzle. You can play it for the game or the magic trick, squeeze it, the lemon any way you want to. Okay? And so here's this game invariant. We talked about that after each of my turns. Both ends will be initially even, initially odd. And so there, the sum is purple by 1. And so you get it in purple by 1 to imitate the moves. The lessons learned. Here's the invariant we talked about. I always guarantee after my move, the invariant is there's two purples. Always. That's the invariant. Dynamic programming is how you'd code this together. The greedy algorithm, but remember, be careful. You will lose to a greedy algorithm. You just always pick the bigger one or the biggest difference. You'll lose. You will always lose thinking that's always going to win for you. So it's great. If you want a greedy algorithm, a case where greedy algorithms fail, this is a great case for that because it's very easy to make cases where a greedy algorithm fails. Looking at kind of this is the thinking out of the box. Rather than the numbers, you look at the locations. That's a very different way of thinking. People always focus on the numbers. But now how about just looking at odd even and where are they in this interesting way? And divergent thinking is part of how to get to that. Okay? All right, last one, next one. Yes, question, go. Bink.
Not quite sure, but it seemed to me that I didn't realize you were copying,
Oh, good. So I did a good job in acting. Thank you.
It was less obvious that since you had 2 rows.
Yeah, I didn't mean to. I mean, it's better. I did this because I wanted to write the numbers big enough, and so that's why I made this there. I didn't want to imply some semantics about left, top, and bottom.
One long row might be easier for one of us to have seen that.
I agree. Yeah. Oh, I like that. That's good. Thank you. I'll use that in the future to have more rows because it's hard to tell which is left. You get confused about left and right. Well done. Thank you. That was very fortunate. I didn't intend that to be, but I wanted to kind of push it and say rather than have 10 numbers, have more than that, which we have. Okay. This is a really fast one, so that was 2. And I'm trying to get to a lot. So give me time checker, timekeeper, how are we doing? 15 minutes, all right. Phew, I'm not going to make it through, but all the slides I had on the first slide. tinyurl.com/CSTA magic. It's all yours. All these are yours. Creative Commons license. Enjoy. Teach in your own classes if you want. So math magic, I take a dice. I didn't bring dice, but it's an easy trick. It's so simple I didn't want to bring the dice. Here's a cup of water. I take the dice, I shake them, I drop in the water. I look down, and I see a 6 and a 3 underwater. And I say, I know what's in the bottom of these dice. I know the sum of the bottom. Like, how's that possible? And then you say 5. And they're like, it was 5. How did you know that? Now, many people who have played dice, looked at dice, they know why that is, and people are nodding in the room. If you don't, it's pretty cool. Like, how is that possible? How many of you know why I did that? 1, how I got to 5? Okay. Sorry?
Is the other side of the 6 always a certain number?
Yeah, there we go. The other side of the 6 is always a certain number. It always adds to 7. So that's the key is how did I do it? And I say 1 and 4. I can either reveal what the sides are or tell you the sum. And the beauty is this is I spent 3 hours in PowerPoint trying to make this picture, so please appreciate this lovingly. Here's the die, and if you look in the mirror, see with the faded transparency with the mirror. I was 3 hours, I'm telling you, with the glowing edges. That was a good 3 hours well spent. 6 and 1, 2 and 5, 3 and 4. It just always works out that way. So they're complements. It's really beautiful. So it's a very simple thing where you can always tell what's on the bottom of dice if you do that. So the answer is 7 minus die 1 and 7 minus die 2. It's very simple. But it's a nice, cute thing. And if you don't know that, for little kids, it works really well. They're like, you're magic, dude. And they, no. And you explain this principle, and there's this kind of thing. And again, they're invariant, a very simple algorithm, and it's really nice design in terms of how the pips of the die. By the way, there's a fun game. If you have little kids, I know Steve does, but if you have little kids like I do, there's a game called Math Dice. There's like a dodecahedron dice, like from Magic, and you roll it and it comes to like 14. And then you have like 5 other dice of very bright colors and rounded edges, not sharp edges like this guy, but nice beveled rounded edges. And they go, and roll these out, and it's like 1, 2, 3, 4, 4, 3. And then you have to cluster them using either multiplication, addition, subtraction to make the goal number. So 14, maybe 14 is maybe a 4, and then a 4, 3, 2, 1. That's a 10, and a 4 is 14. Hey! And then you push it forward, and you get credit for that one. And then you scramble again. Well, maybe 4 times 4 minus, and you do this. And so basically, fluency with numbers in your head is what you're trying to teach. All the dice are normal dice, except for one of the dice, which they gimmicked to get more 4s and 3s, so it doesn't follow this pattern. So pay attention to your dice. I'm just saying you, not every dice follows the right pattern. It's a really beautiful pattern, and not all the dice follow that pattern. So there's that. Okay, numbers game. Anita, I'll take this piece of paper. Here we go. This is a great game. So here's what happens in this game. Magician writes numbers on paper, turns them over. Participant picks random one. Magician guesses number. So here's the number. I write all the numbers on the paper. There's 10 papers. You, the audience, pick one, and I say what the answer is. Let's try it, okay? Here we go. So can I stand here? So I'm going to rip this into 10 small pieces of paper, and I'm going to ask for, I got the front 2 rows. Let's go to the next 2 or 3 rows. Hopefully you realize that I can't put plants in every seat. And now here's 10, okay? And you're not supposed to see that you're too close for the magic to happen. So you need to turn to the side, turn your head, and cough if you can. All right, now let's go here. Give me a number. 7, okay, 7, all right, put that there, very good. Next. 17, okay, 17, bam, okay, go ahead. Third row, third row. 36 is always, this one has just junk on the back. Ignore that junk on the back, because this is where my notes from before. Yes, go ahead. 55, okay, bam, go ahead, whoops.
101.
What? 101. That's California, 101. I love the connection. That's one of our big roots. 101. Perfect, okay? Put that there. Whoops. Put that there. Go ahead. Yes? 14. Love it. Very nice. Lucky number 14. Okay? Go ahead. Yes? 8. Okay, good. Yep. Going back more. Yes. Back. Some back. Go ahead. Anybody? 3. And 3. Love it. 3. Got that one. 3 and 14, another 14. Okay, well, 2 14s. I'll double my chances. I like that one. Go ahead and right there, yeah. Another 7. Okay, great. Double 7s too. Okay, good. So here we go. Is this? I need a volunteer. Please come and volunteer to the audience. I'm going to stand over here. I'm looking. I'm doing a thing. Pick a random one. Show it to the audience. I'm thinking. You show it to the front row. Show your fingers too to tell them what it is. You picked 7.
Get out.
Okay, was that a 7? Don't look at anything more. Did I get it? I wrote 7 on all of them. I love this trick. So how it works is you tell me 49, 124, and I write 49 on every single one. But Dan, this isn't CS. Oh, yes, it is. Here's why it is. The HCI Design Principle says that your mental model of something, of how a system works, should be reflected in the display or visualization of that system. If you're a pilot and you care the most about altitude and pitch, then I better reveal altitude and pitch as clearly as I can and not try to hide that behind some jumping, smiling paperclip, okay? Critical systems need to reveal the innards in a way that makes it clear to the user what those innards are. For example, if you've ever taught Python, Python has sharing of internal structures. I make a list, and then you make a list, and you and I actually point to the same list. But then you don't know that. Your mental model is not that. You think they're different. And now, later on, years later in your code, you change one list, expect the first one, the other one to be the original one, and it's not, because they pointed to the same list. So your mental model was different than the actual machine model. Python has this wonderful thing called the Online Python Visualizer. It came out of MIT, out of the CSTA group, and it lets you visualize. You copy your Python code in here, and it will show you all the data structures, including all the sharing that's happening. That's beautiful, because for the first time, the underlying mental model of what's actually happening with memory is being revealed. You had a different mental model for what I was doing. I never promised you I'd write different numbers. I never told you that. I told you the legal correct. I was going to write numbers on a paper, and I was going to guess your number. I never said, I will then copy your thing, right? So there's also some legalese to this, which is that I never said I would say, for every number, I will copy that number. I never give the whole algorithm. I give you a handsy, you give me numbers, I write them down. I did write them down. I wouldn't say which exactly I was right? So part of it gets to the HCI Design Principle that your mental model is different than actually the correct thing that was happening, and that can happen in systems that are mission critical and life critical, and we as systems, as computing professionals and computing students, need to be revealing the innards in a way that's most useful to the user. Okay? So, i.e., make this transparent. Then you see what I'm writing, and then all of a sudden what the algorithm is doing is clear to you, because then you'd see through that to that. Yes? You had a point.
You could also segue into an ethical discussion.
Oh, I love the ethics. Go ahead, bring it in. Sure, I love it. Ethics.
I mean, I'm modifying your data to suit me. Is that ethical?
Right. Sure. You know, this happens a lot in, I heard the way Dropbox saves space is that if you upload a big file, let's say you write this huge file and you share it with a friend, legally, it's you owned it, and you share it with a friend, you upload it to Dropbox. Your friend uploads it to Dropbox. Dropbox says, those are the same file and only keeps one copy. Why would it keep 2 copies unless it has to? So it actually does. You think that internal Dropbox is making 2, but it says, no. Across all the files ever, it's comparing them all, and whenever it can save one, it saves them and shares the local. It makes sense, right? If you're going to build a system, you wouldn't have 1 million copies of the same thing. If all of a sudden somebody gets a copy of the Titanic on video and decides to upload this illegal version, you keep one illegal version rather than 5,000 of them if they're really big, right? Makes sense. So it's very clever and different from your mental model of what's happening. So in the same way, maybe you might say it's below the abstraction layer, you don't care, but it's important that you can think of some ethics. You know, what is that full contract? Did anybody read terms and agreements of every single thing they clicked? Nobody does, right? This is what I'm doing. In some sense, what I just did was reveal something that was in the terms of agreements you never read. Right. I mean, I could have given you 40 pages and you wouldn't have read it, and I give the trick, and I would have said, it was in the page 37 that I was going to write, I have a chance to write anything I want to. But nobody read it, right? So it gets into the issue that is real in real life with them.
The form where we said we could be photographed.
Yeah, right. Who read the photograph thing? I could be photographed. Yeah, who knows? Yes.
I think it's great because students ask me, how do you do it?
Right.
And it's however you want to do it.
Right.
And so this allows them to do it however they want
That's
to do
exact.
it.
Right, below the abstraction line, it's beautiful, right? Here's the spec of what I expected, and how do you do it is up to you. It's the beauty of abstraction. It's really the beauty of abstraction that we teach that.
It's also why you want to see their code.
Yeah, that's right. Now I want to see why you did. Right, that's the reason we look at code too, right? Not just the output, right? That's very funny. Yes?
Display formulas, please.
Young kids get all excited about math, and then they go to a regular school and they don't do that.
Oh, interesting.
Just
Huh.
curious, because I used to do some of that kind of stuff and get in trouble because
Didn't look at the code. I give a personal story. This is on tape now. My first CS teacher, I was, a good CS programmer. As my first, I was a, high school senior. I loved it, and I was the CS guy for the class. And so he was giving a new assignment, and he asked for the first 10 Fibonacci numbers. And I knew I could do it, but I wanted to see if he was going to look at my code. So it was in BASIC, and so I literally wrote out print 1, print 2, and I typed print for 10 things, because he never said to write it for n. He just said print something that generates the first 10 Fibonacci's. So in some sense, I was holding strict to the purity of what he asked for. He never looked at my code. He has never known that I never wrote the Fibonacci program, but I did what he asked me to do. First 10, print first 10. Hey! So I feel very cathartic right now. I feel very good. That was a wonderful experience. I need a hug. Give me a hug. I feel very different right now. That was wonderful. That was wonderful. How are we doing for time? How are we doing? My timekeeper. 5 minutes. Well, I probably should stop. I've got 26:42. I've got, 16 more to go. Pages of slides of wonderful things, but I don't have 26. I could skip to one more quickie, or we could just talk. Should we talk for 5 minutes about how to wrap this one up and kind of bring it? Does anyone have one they want to share? Does anyone have a magic trick they've used in the past that has... Yeah, please, go ahead.
The binary card trick.
The binary card trick. Tell me what that is. Is it guess the age game where you have 4 to 5 different cards and you pull out the card that has your age in it, and I look at the cards very quickly and I tell your age immediately? Is that the one you're thinking about?
Black and white.
Oh, tell me the binary card trick.
The number from 1 to 63, whatever's on your card.
Okay.
Is it on this card? And if they say yes, you add the power of 2.
I have that. I have it. Excellent. That's a plant, and I actually have that. It is exactly cards. Find the card. I think it's this one. No, that's not it. So close. I had this. I go to slide. Guess your age. There. This one. This is okay. So here's the one.
Yes.
So pick a number from 1 to 15 in your head. In your head, don't tell me. Pick a number from 1 to 15. Tell me what card it's on. And I'll even turn my head. Just tell me. Tell me what card it's on.
C.
It's on C only?
Oh, no. B, C, and D.
B, C, and D, 7. Fast. How did I do that so fast? That's another fun part of this trick. How did I do that so fast? Powers of 2, and this is a nibble. You're giving me the bits of a nibble. 8, 4, 2, 1. And now I'm basically saying, you gave me that, and that's a 7. So it's kind of fun. So that's a fun trick to do with this. It's also a fun trick to do. With larger numbers, I can't just do them in my head. If you just tell me A, E, F, and B, I couldn't do that so easily. But for the nibble. Yeah. And if you can do this from larger cards for ages is a fun thing. You probably should do this for maybe 1 more card to get the ages of your kids in your class. So maybe 5 cards, and all you do is look at the first number, because that's the first number in each one. So you tell me this, and you say, oh, it's on C and D. So I pull those out and I look at those 2 numbers, it's 6 very easily. It's kind of nice. So this is a good one. Great. Yes, more. Come up on the microphone, because people can't hear you on the film, and this is being archived for 150 years on the CSTA server. So that's... Okay. I didn't mean to, but they can't hear you.
Well, I do one that's called the algebraic calendar, and you're supposed to pick 4 numbers on the calendar. They can pick any 4 numbers on the calendar, and then it's kind of an algebraic equation. And I forget what the 4 numbers equal, but basically you're using a algebraic problem to figure out, you obviously know whatever number they have to give you, I think, the beginning number. You can look it up, but they have to give you the beginning number, and then you can tell them what,
The remaining numbers are?
yeah, and it's basically because you're taking, the x is representing the first number, and then you know x plus 7 is the number below, and then x plus 8, and then x plus 1, and then,
Oh, I see.
I think
it's
they
like
have to give you the
magic square
total.
in a way, where you kind of give me a thing, and there's a pattern based on the first number, what the other numbers have to be.
Yeah, and then I have them kind of come up with their own, like, using the calendar, but like maybe they pick a week or you do something like that. So.
Wonderful. That's great. Thank you for that. Thank you very much. Okay. Yes, you have one? Come up if you don't mind, to just so we get this on camera and archived. Thank you. This is great.
I've always loved the problems that at first appear to be impossible and that are actually doable. You can do this with real problems too. Public key encryption is a problem that if you present it right, appears to be impossible and yet can be done. And you can do it just by screaming across the room. The CS Unplugged website has a beautiful one. Onion routing, the thing Tor is intended to solve. How do I connect to a website without them knowing how to connect, that I connected to it? I mean, this segues perfectly to that. Onion routing, yeah, the Tor, T-O-R. Just look up Tor and you'll find it. Tor, T-O-R, it's an acronym for the onion router. It's hard to code, but it's an interesting technical problem.
And then if I look on the screaming across the room encryption,
It's called public key encryption. You can do it by screaming across the room, but what you're really doing is some calculations on paper.
I just went through these 2 days ago, and there's a sequence of exercises 14, 16, 17, and 18. The last 3 and 14 to set it up are what you use to get up to the big one, which is PGP at the end. And there's the Peruvian coin flip, which is the one before. They're all really good. So these last 3 are really outstanding in terms of cryptography, but they're just really good. So CS Unplugged has done a great job. And also, I mean, I really appreciate they spend a page describing to the teacher, here's what's going on, here's the CS behind it. It's just really important, which I try to do here as well. So it's good stuff. Thank you for that. It's a good suggestion. How are we doing for time? Closing it out. All right. Well, thank you so much, folks. I really did time. That was really great. That was really great.